CTPNP 2019, and now we move to the second session. Today in the second session will be about physics research and education in the US. The speaker for this session is Professor Umar Mohideen from University of California, Riverside. For your information, he is one of faculty members in University of California, Riverside. I'll read some CV from Umar Mohideen. He is professional honors, fellow American Association for the Advancement of Science, fellow American Physical Society, and for university honors, Senate Distinguished Campus Service Award 2014. And for his publication, total of 100 peer review articles and 10,463 citations, H index 43. And his research funding agency, now current funding, is US National Science Foundation. About his research area on experimental condensed matter physics. Now, Prof. Umar, the floor is yours.
Thank you for the introduction, and thank you for the invitation to come here from Dr. Latifa. She was very persistent. She emailed me many times, every week, many emails, till I said I will come. So, very, very persistent. So thank you for the invitation. So she said I will I was invited to give 2 talks, and 1 scientific talk and 1 public lecture talk. So I thought for a few days about what my public lecture talk would be useful for you. So I decided that, and she said for the public lecture, most of the audience would be students. So I wanted to give a talk that you will take away some useful information, because I will be talking about my scientific research tomorrow. So I decided to talk today about physics education in the US, and how you all can participate in that, how you can take advantage of that to learn more. And I want to emphasize that this is my perspective. I do not represent the government. I do not represent the state of California. This is just my perspective. Okay? So I'm from the University of California, Riverside. The University of California has 10 campuses for research universities. There are 10 research universities in California. The oldest one is at Berkeley. It's called the University of California at Berkeley. So we are a newer campus. We are based in a city called Riverside, which is close to Los Angeles. It's about 60 miles from Los Angeles. Okay. And so I want to start out. I will tell you maybe a little bit about my Department of Physics and Astronomy. And I want to tell you about how I appreciate that all of you are doing physics. As you can see from this morning's talk, Professor Lee, Professor Haryanto, and others, how much they enjoy physics, how much they love doing physics, and how much they talk about physics, especially the energy of Dr. Haryanto. So you know, I want you to understand how much there is to do in physics left, and I want you to understand how, by using the opportunities in US and in Europe, you can really get to understand why we are all so enthusiastic and why we all have a passion for physics. Okay? So that's my idea here. So why study physics? So it's, you know, we like to point out, if you study physics, you can go into any career you want. Okay? And more importantly, it's a way of life. This is a way of life. Physics is a way of life. And this is some of the passion you have seen in this morning's lectures. Okay? Now, so I want to start with a quote from a physics administrator. This is, his name is Fang Li Shi. He's an astrophysicist. He was a vice president of the University of Science and Technology of China. And he's also a dissenter. I mean, he left the country because of political issues. And he wrote an autobiography, and he talks about the impact of studying physics, particularly in China. He says, the Chinese Communist Party officials asked me many times why it is that students stray from communist ideology when they go to college. Where does the counter-revolutionary education come from? They tied themselves in knots trying to figure out why students who were carefully selected for good thinking when they entered universities turn into bourgeoisie intellectuals. So once they were there, they took out magnifying glasses to examine every detail of campus life inside and outside the classroom and asked school administrators to remove anything that came remotely close to counter-revolutionary thinking. But it never worked, and can never work, because what they call counter-revolutionary thinking is stuck inside of science. No course in a physics department is more counter-revolutionary than Physics 1. That's physics, introductory physics. No one who understands physics can turn around and accept a claim that Marxism-Leninism is a special wisdom that trumps everything else. So this is, you know, to me, this is a very important message about why you study physics. And I don't mean politics. I don't have anything special against Marxism-Leninism, but for Marxism-Leninism, you can substitute any political ideology you want. But once you study Physics 1, then you know how to think through any issues that you're confronted in life. That's a message that he wants to make. Okay, so it is really, studying physics is really a way of life. So in California, we have 10 campuses for the University of California. And all those 10 campuses are excellent campuses, starting with the University of California, Berkeley. And we are a smaller campus. We have about 44 faculty in physics, which I understand is the same size as the number of faculty here. So we have 44 faculty. We have many faculty with senior awards. We have a Nobel Prize winner. It was Barry Barish, who won the Nobel Prize a year ago. And we have many faculty with other prizes in the department. So what we aspire, I'm going to tell you what our goals are in the Department of Physics and what we want to do with the department. So we have a goal that the whole mission of the department is to teach students. Okay? And then I'm going to tell you what we mean by teaching. So we have 181 undergraduates. So they divide into 4 years. So we have about 40 to 50 undergraduates a year, which is a small department. And we have about 140 graduate students who are doing the PhD. Okay? Because the goal is to excel in education, which means includes teaching and research. Education is not only teaching, but includes research, because we're educating PhD students, which is research. Okay? So in terms of undergraduate education, and this is important because what happened in physics in the 1990s in the United States was the number of physics students went drastically down. So the American Physical Society, which is responsible for making physics policy, did not understand why nobody was taking physics in the US anymore. So they sat together and thought about this, and they came up with changes for the physics curriculum and how we teach undergraduates in physics. With the result from 2000, the last 20 years, the number of physics graduates has increased tremendously. Okay, so this is something very positive that happened. And the reason that it went down in the 1990s was because of the rise of computer science in particular. Students who used to do physics now started doing computer science. And number two, the end of the Cold War. The end of the Cold War meant that funding for research, particularly for physics-oriented research, decreased, which meant the number of physics students was supported for a PhD decreased. So those two reasons meant that number of physics students went down. So the physicists in the US decided to figure out how to increase the number of physics students, and this is how we did it. And I'll tell you how this worked. So what we do is, first is we changed how we teach undergraduates. So we don't teach undergraduates anymore by just giving them a sheet of problems to go home and work at. We work with the undergraduate students in the classroom, trying to do the problems for them, and then give them homework afterwards. So the number of hours of interaction with the faculty and students was increased by a factor of 3 to accomplish this. So the professor stays with the students 3 times as much hours so they can do the problems with them and teach them how to think in physics. Because thinking in physics is different from thinking in other subjects, particularly if you're a mathematician, you think differently from a physicist. If you are a biologist, these are all very good sciences. Biology, chemistry, physics, and mathematics. These are fantastic sciences, but you have to be taught in the first year of your undergraduate how do physicists think about a problem. And we did this by increasing the number of hours of interaction between the undergraduate students and the professor. And the other thing is we introduced professional development. That is, we tell the student, even in the first year, what kind of jobs they're going to get with a physics degree. Okay, and I'll tell you where to find that information. And the most important thing we did was make sure that as an undergraduate, even as a first-year student, you are involved in research. So every undergraduate is encouraged to research with a faculty member. And I'll tell you how we accomplish this also. Okay. So the first thing is we pointed out that a physics education is applicable to any career. Okay. Physics gives a broad, multi-skill education. And you can go to this website. APS stands for the American Physical Society, APS. And if you go to this website, you have a listing of all the jobs that you can get with a degree in physics. Okay? And for example, there are people with videos there who will tell you they went to do business after a physics degree. There are people who become comedians after an undergraduate degree in physics, and they tell you how physics education was useful for them. There are videos of people becoming cartoonists. There are people with a PhD in physics. Okay? Then, of course, there are doctors, lawyers, and engineers who all got their undergraduate degree in physics, and they tell you why physics education is the best thing that they did. Okay? And the other important thing we always stress is physics students who major in a physics degree in the US always get the highest scores in the medical school exam and the law school entrance exam. Okay? And there's a reason, because when you get a physics degree, you are forced to think rigorously, logically, and with confined number of axioms. So that forces you and gives you a very rigorous education. And that's why people with physics degrees do so well in so many different fields. Now, and the other thing we did was every first year physics has to take a class which forces them to look at jobs in physics, careers in physics. They have to, in the class we teach them about general physics, how it applies to energy conservation, how it applies to climate change, how it applies to nuclear physics, nuclear issues, the issues that confront us as a general person. not as just as a physicist, a general person. So we force them to learn about this. So in this class, every faculty member gives a talk, and the student learns to know about the research of every faculty member in the department. And the students are given credit. The way they pass the class, they have to go and interview a faculty member. So every student to pass the class has to go have an interview with a faculty member and take notes. And some of the questions we tell them to ask is why they do physics, why they do that particular area of research, what is interesting about it. And they do that interview and they write a paper, and that's how they pass the class. The students also make a presentation on what kind of job they'll want after they finish the degree. And they learn to write a resume, how to look for a job. Okay? So they do this in the first year, first semester. So they pick a favorite career. You can be a cartoonist, you can be a journalist, a science journalist, whatever they want, and they make a presentation of why they want the career after they get a physics degree. So that's about undergraduate. In terms of the research areas for the physics faculty, we have 44 faculty, as said, and so in the department we have astronomy and astrophysics. So we study inflation, galaxy formation, dark matter and dark energy. So we have about 10 faculty doing that. We have about 13 faculty doing elementary particle and nuclear physics. We have 14 faculty doing condensed matter physics. And we have 4 faculty who do atomic, molecular, and optical physics. And biophysics for 2 faculty. So this is how we break down the areas of research. So in terms of graduate students in physics, the most important thing that I want you to take away is it's free to study in the US. So I want to encourage all of you, if you want to go for a PhD, that you should apply to a US university or a European university, but US is much more open and free to get admission into for a PhD. So it's free, all your tuition fees are paid, and all your living expenses are paid. So all your food, all your rent for your housing, everything is paid by the university if you go to the US. Okay? So all of you should take use of this to apply if you're interested in a PhD. Now, 50% of students in the US are foreign students, 50%, and you can look at this graph. This is the domestic students, the blue line is the domestic students, and the red line is the foreign students. And you can see, after about 2000, the number of foreign students is the same as the number of domestic students, okay? So 50% of the students in the US are foreign students. And nowadays, most of the foreign students actually come from China, from India, from Iran. We get a lot of foreign students from Iran, okay? And a lot of women foreign students from Iran, okay? Which is surprising. And some from Eastern Europe, that's Russia and Eastern Europe, and some from the Middle East, but not many from the Middle East. But most of the students are actually from China, India, or Iran. These are 3 countries that most of the foreign students come from. And I'm talking about, look at the number of foreign students. There are 1,000 foreign students, 1,000 foreign students, just in physics PhD programs. 1,000 foreign students. And these will be in the top 50 universities in the country. Okay? So every university is going to take anywhere from 10 to 20 foreign students just in physics. Okay? We usually admit about 15 foreign students in physics. So you should definitely take care of this opportunity to, if you are interested in a PhD in physics. So, and if you're interested in how to apply and which kind of universities to choose from, this website is a good source of information. The AIP is called the American Institute of Physics, and this has all the statistics about PhD programs in the US. And if you go to this website, you can find out more information about which universities concentrate on which type of research, and then apply to whichever one you're interested in. So typical PhD program in the US is 1 or 2 years of classes, and after that you get your master's degree in science after 1 or 2 years of classes. You do research for an additional 4 years, and you get a PhD. For the research, you need to do original research. Okay, you have to. The criteria is you have to create new knowledge. New knowledge has to be created. Then you get your PhD, and which takes about 3 to 4 years. So, how do you apply for a PhD program in the U.S.? To apply for a PhD program, you have to take 2 exams. Okay, before you apply. So, one of the exams is called the Graduate Record Examination. Minimum score, you have to get about 300 over 340. This is not required by the physics department. It's usually required only by the university. This is just basic English and basic arithmetic. It is just addition, subtraction, and multiplication. Then you have the TOEFL, but the TOEFL you already have in Indonesia, so you know what the exam is. That's about English. But the most important exam is the Physics Graduate Record Examination. And in this exam, you have to get a score close to 800 out of 1,000. 800 out of 1,000 if you're a foreign student. Then you have a very good chance of getting a fully paid PhD program. Okay? You got to get about 800. And you can go to this website, and this tells you information of how to do these exams. Okay, so the physics GRE for admission and scholarship to a US program, you have to get about 80 percentile. And this is something that you should do, which makes your chances of getting a scholarship easy, which is to do some research with your faculty. You should join up with your faculty and do some research, even if it's some simple computation. That's good enough. The faculty member can write a recommendation letter for you, and that will increase your chances of getting financial help when you come to the US. So what is the importance of foreign graduates? So in the US, over 30% of all Nobel laureates, 30% of all laureates who are in the US were foreign born. So 30% of Nobel Prize winners in the US came from another country. They were not born in the United States. It's very important. And this the government realizes. The other important thing is after the internet, 1995 to 2005, 25% of all the high-tech startups were started by immigrants from foreign countries. So most of the new companies, like Google, the examples are here. 50% of foreign firms are started by immigrants. Google, Intel, Apple. These are all companies which were started by foreign-born people who came to the United States to study. Okay? So most of these companies today that you know about, like Google, are run by people who came as foreign students to the United States. Okay? So, and when we talk about patents, if the top among the 10 universities that produce the most patents, more than 3 out of every 4, that is 75% of the patents that are produced in the United States are made by a foreign-born person. Okay, 75% of the patents are made by foreigners in the United States. So, more than 85% of information technology patents, IT patents, are made by foreign nationals. Okay, so that tells you the contribution that foreigners make to the United States education and United States technology. So that's why we welcome foreign students to the United States, because we know that they are going to contribute to the U.S. economy. They are going to be the drivers of the U.S. economy, as it's happened in the past. Okay? So this is a very important thing which we try to emphasize and we try to follow. And you can look up for more information, like I said, at the American Physical Society, which has all the statistics on the contribution of foreign-born students. Okay, now I'll tell you a little bit about how research funding works in the United States. Funding for physics research. So funding research in the United States is given by these organizations. It's the National Science Foundation, gives about $1,500 million. Now this sounds like a... That's $1.5 billion. Now, $1.5 billion, is that a lot of money or a little not too much money? Is that a lot of money, $1.5 billion? Like, what is the GDP of Indonesia? What's the GDP of Indonesia? Does anybody know the GDP of Indonesia? How much is the GDP of Indonesia? How much is the economic activity in Indonesia? It's about $1 trillion. $1 trillion. Okay? Indonesia has $1 trillion every year. The economic activity in the US is $20 trillion. Okay? So this is $1.5 billion. The US budget is $5 trillion. $5 trillion. Okay? That's the United States budget every year. So this is about 0.025% of the US budget. Okay, 0.025%. That's how little money goes to research. Okay, 0.025%. That's $1.5 billion for the national. The Department of Defense gets about, for science, for basic research, they allocate $2.5 billion. The Department of Defense is all the Air Force, the Navy, and the Army. So they give $2.5 billion for basic research. The Department of Energy has $6.5 billion. Now the Department of Energy, again, $6.5 billion is actually only about 1% of the US budget. And what the Department of Energy does with this money is it runs all the nuclear programs in the US. They make all the nuclear weapons and anything to do with nuclear. That's why the US supports physics so strongly, because of its application in nuclear energy and nuclear defense. And then there's NASA, which is the space science, and that has about $6.4 billion. But compared to all of this, the National Institute of Health, which does biological research, gets close to $40 billion. So the support for biology is always much higher than the support for physics and chemistry and mathematics. Okay? That's because the politicians who make this money, who allocate this money, can make a better argument, can convince themselves much more easily if they say they're giving money for human research, for research to improve our health. That's why they allocate so much more money for biology than they do for physics, chemistry, and math. So this is a breakdown of what the US National Science Foundation research is. So you can see the $6.5 billion here from the National Foundation is divided into so many divisions, of which the physics is just the mathematical and physics sciences is about $1.5 billion. Okay? So we get very little of the total research budget. Okay, so what are the US research priorities in the US? So how does this money get allocated? So this total money, which is about $10 billion for physics, how does it get allocated? It gets allocated by what's called a decadal survey. So every 10 years, physicists in the US decide in a committee what are the important research areas in the next 10 years. They try to decide what is the most key questions that need to be answered in the next 10 years. And that's called the decadal survey. So every 10 years they do the survey, and they make a committee to decide what the most important things is, and I'm going to tell you what they decided last time. Okay, so what is a decadal survey? So this is conducted by the US National Academy of Science, which is like the Royal Society. So every country in Europe, for example, has a Royal Society. So in the US, in the equivalent of the Royal Society is the National Academy. So the funding agencies ask the National Academy to come up with priorities for the next 10 years, to rank which is the most important research areas for the next 10 years. And this is required by the US Congress, which does the allocation of the budget. So the Congress is going to look at this before they divide up the money for the research. So in astronomy and astrophysics, the Academy, US National Academy decided on these topics. And we heard some of this today. So first is to understand the cosmic dawn. So what happened when the Big Bang started, as we heard from Professor Lee this morning. So that is the most important subject that the US is going to invest on. In particular, searching for the first stars, searching for how the energy inhomogeneities happened when the Big Bang started. Okay, looking at first galaxies, how the first galaxies formed, and how the oldest black holes formed. That's priority number one. The next priority is looking for planets outside the solar system. So as you know, I don't know if many of you have been following the research, we are finding more and more planets which are outside the solar system. So the question is, we want in the next 10 years, we want to find planets which have a similar atmosphere like the Earth. We want to find planets which have water in them. So the minute you have water, then we understand that they will also have life. So what we are looking for is planets outside the solar system which have a signature for the water molecule or signature for organic molecules. If we find the spectra, the light from organic molecules or water in their atmosphere, then we know there's probably life on those planets. So we are looking for habitable planets. That is the next priority for the US research. And of course, the physics of the universe, which is understanding the scientific principles. And we heard a little bit about that today. Dark matter. We call it dark matter, and dark energy constitute 94% of the universe. Real matter, which is Professor Lee called them metals, but real matter, which is just atoms, which are electrons, protons, and neutrons, and all the other stuff, are only 6% of the universe. So we are only 6%. Everything that we see, all the planets, all the stars that are observable, are only 6% of the universe. 94% of the universe, we have no idea what 94% of the universe is. We know it is there. We know it is dark matter and dark energy. And it's going to be people like you who are going to come in the next few years who are going to tell us what this dark matter and dark energy, which controls most of the universe, is. We have no idea what this is. We don't know what the physics of it is. What are the rules that dark matter and dark energy follow? We have no idea. We are hoping that the next generation of physicists will be able to tell us this. And that's why it's priority number 3 for the next 10 years, how to understand dark matter and dark energy. And then, how do we understand this? So they identified a few areas, a few instruments to understand this. The first one is called WFIRST, which is a Wide Field Infrared Survey Telescope. This telescope has just been launched. So this is a telescope which looks at infrared light, because for visible light, we can observe it from the Earth, but for infrared light, which is long wavelength light, gets absorbed by the atmosphere of the Earth. So we cannot look at infrared light very well. So we have launched a new telescope called the WFIRST telescope, which is outside the atmosphere, which is in space, and can look at infrared light. And as pointed out this morning, because these are long wavelength, which means that you can look at Doppler shifted light even from hydrogen molecules and hydrogen ions, not hydrogen molecules, but hydrogen atoms, okay, which are Doppler shifted, which means that they're moving very fast, so we can look at light of long wavelength, so we'll be able to do the first part of what the decadal survey says, which is a look at the cosmic dawn. So that's why this is a priority. The next is to look at is a laser interferometer space antenna. So we're going to put 4 telescopes up in space, which make what's called an interferometer, okay? And we can look for gravitational waves. And so when a gravitational wave comes through, the interferometer will be modified. The arms of the interferometer will change, and we can know a gravitational wave went through. So we can look at aspects like what Professor Hayatano was talking about this morning, such as the collapse of black holes. We cannot look at that. So that's priority number 2. I already told about looking for planets outside the solar system, which is look at spectroscopy of the atmosphere of these planets, look for any liquids, particularly water, that might exist in the planet. That will tell us that there is life on this planet. Not life like us, it might not be humans, but it could be any other form of life. Life based on maybe some other form of DNA, maybe for some other molecules. Maybe it's not an oxygen-based life, it might be a sulfur-based life. But life, we know, is just a chemical process, so it has to exist where there are appropriate conditions. So if there is appropriate conditions on some other planet, it has to exist as well. Okay, that's the conclusion. So we're looking for life in other planets. And last of all, I'm going past here. So we're going to look at the as Professor Lee talked about this morning, look at inflation in the universe. What happened right after the Big Bang? So when right after the Big Bang, the universe went through a period of rapid inflation, and we have no idea, no signature yet of how to study this inflation experimentally. And that's another priority of the National Science Foundation, is to look at signatures for the inflation. So these are the priorities in astrophysics and astronomy. And the important thing is, if you're interested in any of this, all that you have to do is to email. Every one of these experiments has a foreign representative, a representative for people from other countries who want to participate in these experiments. All that you have to do is to email them, and they will help you navigate how to participate in these experiments. Okay? So you should not be afraid of emailing people and telling them that you're interested in this research and you want to participate in this research. All these programs, which are very expensive programs, but you don't have to contribute. They will welcome your participation, because the goal is to make sure that everybody can participate in exciting physics research, because we know that everybody can contribute to physics. It's not restricted to people in the US or Europe. Everybody can contribute, and everybody can make an important contribution to any one of these fields. Okay? So just go ahead, look up these things, and email the people who are working on this, and then they will welcome your participation. Okay, in terms of particle physics, like I told you, what is dark matter? We call it dark matter because we cannot directly observe its effects. It does not give out light. That's called dark. So it doesn't have a very strong electromagnetic interaction. So we call it dark matter. But we can infer its existence from other processes, like the rotation speed of galaxies, for example. We know that dark matter exists. And we also know from these new supernova experiments which were done in the early 2000s, which Professor Lee talked about. We know dark matter and dark energy exist, so we need to understand that. So why is the universe expanding, and why is this expansion accelerating? Dark energy. So we need to understand what dark energy is about, how to make experiments to observe dark energy. We have no idea about dark energy. At least with dark matter, we can observe it through gravitation. But dark energy, we have no idea how to observe dark energy. What are neutrinos, and what are their masses, and what is the impact of neutrino masses on cosmic evolution? Is this physics outside the standard model? Professor Lee talked about this morning, and this is one of the main questions we want to answer in astrophysics and astronomy and particle physics. So again, I talked about this earlier. What happened when the universe went through a rapid inflation at the start? How do we do experiments to look at imprints of this rapid inflation? So those are some of the important questions that the US Science Foundations want to answer. In condensed matter physics, how do complex phenomena emerge from simple ingredients? And magnetism is an important subject in this. And how will we generate power in the future? Are we going to use clean energy? Are we going to use nuclear energy? What are the potential possibilities of using different forms of energy, and how this interacts with physics, understanding the physics of power generation? What is the physics of life? You know, biophysics is a very important part of physics. Since physicists are the ones who understand the basics of how atoms interact, we need to understand the physics of life. Is the life that we know about, the DNA molecules and all the chemical reactions that we know about today, is that the only form of life that we can have? Are there other forms of self-propagating molecules, which will be life as well? And so what is the physics of life? So, and what happens far from equilibrium? What happens with non-equilibrium effects? Okay, these are the questions that they have identified for condensed matter physics. So, in terms of particular research, they want to understand the research into metals, alloys, and ceramics. This would be very applied. In terms of quantum materials, the science and engineering, superconductors, semiconductors, magnets, and two-dimensional and topological materials. This is a new area of physics that's come in recently in the last 5 years. And they suggest that the National Science Foundation to develop a new type of center that will enable and stimulate students, faculty, and industrial scientists and engineers to work side by side. So they want students and faculty and engineers to work together. And support centers to develop new computational and advanced data analytic models, new computational methods to do physics. Okay? So these are the priorities for research in condensed matter physics. So in terms of faculty participation, they're not many. I want to spend a few minutes. Again, every big research program, be it a telescope or a Stern accelerator, will have a foreign representative, foreign liaison. You just have to contact this person. If you go to the website and you look up for this person, you can just contact them, and they will welcome you to participate in any of these big experiments. Okay?
If you're a faculty, you can also participate in this, what's called the Fulbright Program, which is a special program for faculty to apply with a master's degree to come to the United States and stay there for 2 to 3 years to do research. Okay, that's a Fulbright program. So I just want to end with this. So, the goal for all of us here is to inspire and teach others about the importance of physics. Okay, and so physics describes and shapes the world we see. So everything about what we see has come from physics. Every piece of technology that we use and do has come from physics. So many of us benefit from the torrent of new and improved electronic devices. But few people are aware that these products are the fruits of rich and coherent discipline characterized by a mix of fundamental and applied research, which is physics. Few people understand that the cell phone that they use today comes from basic physics research done somewhere else, some time ago. Okay? And it's our job to tell them the impact that physics is having on their daily life. We have to propagate this. So we have a very limited public awareness and understanding of science, which is an increased danger to our nation's economic security. This is, of course, referring to the US. This is a report from the National Science Foundation. So when people don't understand science, people don't appreciate science, it's going to impact national security. Okay? And it's dramatically reflected in the current crisis in primary and secondary school education. One of the big problems that foreign students, and I had the same problem when I came to the US, is we think somehow the undergraduate education in the US is much superior to what you do here. That is not true. Okay? You have to understand that what you are doing in physics here is as good as what we do in the United States in undergraduate education. Okay? So you should not be afraid to apply and come to the US. Because in the US we have a problem that high school students in particular do not do much science. They would rather do subjects which will be easier and easier for them to get good grades, and therefore they'll avoid subjects like physics. So that's one of the problems we have, and that's why we invest so much time as faculty in science to go out to the high schools to teach students of the importance of physics. We go out to the high schools and tell students why physics is important. Okay? So you should not be afraid to apply to the US. Your education is as good as any. Okay? And our goal, even whatever country we are in, is to improve general scientific literacy. We have to improve the science knowledge of everybody so as to increase the pool of students interested in science and engineering. Okay? As long as we increase the number of students who are interested in science, we will get people doing better and better science. As long as we have more people in the world doing physics, the amount of physics that is done is going to be better. Okay? As we have more people from Asia doing science, there's more physics going to be done. Particularly, as you've noticed, as China has grown, China does more and more physics. This is very good for everybody because the knowledge in physics is going to advance because now a lot of Chinese are going to do physics. As the rest of Asia does physics, this is going to be good for everybody because we're going to have more and more intelligent people doing physics and advancing physics knowledge, which is the basics for every knowledge in the sciences. The physics knowledge has to be advanced. So we have to educate everybody to do more and more rigorous science, in particular physics. Okay, so that's one of the goals for the decadal survey. So how to inspire and educate? How do we do this in the United States? So we send undergraduates, which are students like you. We send the students like you to go to elementary and high schools and tell the elementary and high school students why they are doing physics and what is so great about physics. Because if the students in high school and elementary school hear from their own peers, people who are 1 or 2 years older than them, the brothers and sisters, then they will understand better than the parent telling them. If I go tell my children to do physics, they're not going to listen to me. Okay? But if my older son tells his brother to do physics, that is different. Okay? They will listen. Okay? So it's very important that all of you go to high schools and elementary schools and tell your brothers and sisters about the important basic role of physics, okay, and how that shapes human society, okay, how it's going to shape technology, okay, how it's going to change our life for the better, okay, and it's going to come from the rigorous sciences, which is, math, physics, chemistry, and biology. Okay, so that's what we got to do. We got to visit elementary school and high school and bring elementary school and high school students to the physics department. So we bring the high school students, elementary school, the physics department, and tell them why physics is important, why they should do physics in high school. When we have special events, we bring out Nobel Prize winners, or when we have the Nobel Prize given in physics, a faculty member of the physics department will give a public lecture to all the parents who are non-physicists. We invite parents in the public to come, bring the children to come to this public lecture, which will tell them about what was important about the Nobel Prize research that was given. Okay, so to get the children excited that they can one day be winning the Nobel Prize. So we have city and university-based public events. So the city usually sponsors public events in physics. So we go out some local place in the middle of the city, and the city will announce that there's a public exhibition where we will do simple experiments in physics to tell people about the importance of physics. And also in some cities, we have museums where children can go and do some simple experiments day to day, where they can learn about the basic physics, okay, about sound propagation, light propagation, lenses, different things, simple things they can learn. The best one is the one in San Francisco, which I have a website for. And the website will tell you about the simple instruments you can make, which can educate children about the importance of physics. Okay, so that's the end of my talk. So I'll stop here and take any questions you might have. And thank you for listening.
Give applause to our speaker. Thank you very much for your invaluable information present to us. Ladies and gentlemen, now we move to the question and answer session. If you have a question, please raise your hand and don't forget to mention your name and your affiliation. Any question?
Okay, thank you for the time. Sir, I have a question. You are from India, right?
Yes, originally from India, okay. Yes.
So, what is my question is, how it could be possible that India has the development of science and technology much better than the other average developing countries? What it could be possible? And then I need your opinion, because I want to continue my study in India. And your opinion about the possibility of nuclear war between India and Pakistan. Okay, thank you.
I can give you, again, I'm not a politician, so I'm going to give you my perspective. That's why I said first. To your first question, why does India have a more developed science infrastructure? This is your first question. We were actually talking about that with lunch with some of faculty from here. When India was ruled by the British set up educational systems about 50 years before, or even 70 years before they did this in Indonesia. So in India, the universities started in the 1850s, 1850. They set up universities. Again, the British were a colonial power. They did not set this up because they want to help the Indians, right? They're colonial powers. They set this up so they can have a bureaucracy to manage India while they are at the top. Okay, so they set up a system, but they set up the system very early, 1850s. So we have many generations of educated Indians. Okay, and remember, India has 5 times the population of Indonesia. So this is a big statistical factor you always have to keep in mind. Okay? So India's had many generations more of education than Indonesia did, Western education. Okay, so this is the biggest factor. And the second biggest factor is when India gained independence in 1947 from the British, it already had an education system. But at the time, we had a prime minister whose name was Nehru. And he realized the only way for India to move forward was to set up universities in science and technology. Okay? So the first government itself decided that they have to set up science and technology universities. And they asked for help from Europe. So every country in Europe, including Russia, set up its own university, okay, in science and technology. So these are the major universities that you have in science and technology in India now. Okay. So that was a big recognition. And this was, it's not something that India came to itself on its own, because Russia did this about in the 1920s already, 1920s and 30s. Russia invested a lot in science, particularly in physics, okay, and developed it. So this was something that was already there, which was already understood, that if you want to grow very fast, you have to invest in science and technology universities. And this is nothing special. I told you that a lot of foreign students come from Iran. And the reason Iran has progressed so much is after the Islamic Revolution, Iranian the government set up a lot of universities in science and technology. And they developed science and technology rapidly. So we have some of our best students who come from Iran, both men and women. So it's a policy which is set up in some Asian countries, and this goes for Japan, and I don't know for Korea much, but which have focused on setting up universities in science and technology. So that's why we have many more. It is nothing magical. Okay? No country has a monopoly on good science. Everybody can do good science. You just have to have the educational infrastructure and the opportunities to do science. You have to have, particularly in a field like physics, where it's experiment-based. So you have to have the experimental basis for doing physics, which is very expensive, and which is also culturally very hard. Doing experiments is a cultural change. You have to work with your hands. And this is not something that is taught in high school. In physics, you have to do everything by hand in experimental physics. And this is a cultural change, which undergraduates get used to by doing labs, by doing laboratory. Okay? Because in experimental science, it's expensive. Experimental science is expensive. So only rich countries can afford the experiments nowadays. But you can do theoretical science, which is a lot cheaper. So you see, in India especially, there's a lot of theoretical science than experimental science. But if you want to do experimental science, it's easy to go to Europe or the US. It's not that hard. You just go to Europe or the US. And it's no such thing like one experimental science is better than theoretical science or vice versa. If you like experimental science, you should do experimental science. Just go outside. Okay? Does that answer your question? Okay. And what was the other question? About the possibility of nuclear war. I'm not an expert on that, but I can tell you that we have avoided nuclear war for now 70 years. Okay, 70, almost 80 years. Politicians know the damage it has done in Japan. People understand what happened to Japan, so they know this is not good for any one of us. Okay, and everyone will have to answer for starting a nuclear war. So I don't think every politician knows that they cannot start a nuclear war. Okay, because there is no winning a nuclear war. Everybody dies in a nuclear war. That's a last attempt to survive, and I don't think it will come to that. I think you have to worry, and you have to set in place certain procedures to prevent this. For example, every government has procedures that the president just cannot order a nuclear war. It's not allowed. They have checks. Multiple people have to check off before a nuclear war is started. So you have to set those procedures in place so you don't have one person deciding on a nuclear war. So all these countries have these processes in place. So I'm not so worried about it. Not to say that you shouldn't worry about it. At your age, you all have to worry about this, and you should worry about it because you will be making those rules in the future. And you should make rules on how, if ever a nuclear war is started, that you don't start this lightly. And you have to make the rules. Okay? That not one person will press a button and start a war. That never happens, and that should not happen. Okay?
Okay, that's an interesting question. So, committee will give you a So, any other question? Any other question? Okay, you.
My name is Shabara. Okay, I want to ask a question first. It has been explained that US are doing the projects basically in physics. If we want to apply to be participants, is there any steps that we can be eligible enough to participate or to join those projects? Thank you.
Okay, so yes, you just have to, especially if you have an undergraduate degree, if you have an undergraduate degree, you can apply to join a PhD program by following the steps I outlined, to become a PhD student and participate in the research. That's the easiest way. But if you already have a master's degree or a PhD degree, you have to apply directly to the program. And every program will have a person to interact with foreign researchers. Every program has a person. So you just have to email the person and tell them if you've done research before in that area, tell them what you've done, and they will welcome you to participate in this research and provide you with funding. Okay?
Okay, please.
Thank you. I'm Chita, a high school teacher. Some concerns. First one is research. Our research really contributes to humans' life. Be a better, like really the research makes our we as a side. Thank you.
Well, very good question, very good question. You know, the question is, are we, for example, are we living longer than our grandparents did? Yes, we are living much longer. Are we suffering less than our grandparents did? When we are sick, we can go to the hospital. When we are in pain, we can go to the hospital. Do we have more things than our grandparents did? Definitely better than mine did. I'm eating much more than my grandmother and grandfather did. I'm living longer than my grandfather and mother did. And I want to. I can watch anything on YouTube, whatever I like. I can watch anything on Netflix. I can listen to whatever news I want. I can learn about Indonesia. I can learn about the US. And I can read about anything I want. And I think my life, therefore, the quality of my life is much better than the quality of my grandfather and my grandmother's life. And they did everything for my education. Without them, I cannot be here. But they did this with the idea that I getting educated is good for everybody. Yes? So they did everything for me. Now, so it's all because everything that we do today comes from physics principle. Everything comes from physics principle. Yes? The cell phone, the TV, everything that we do comes from a physics principle, from basic research in physics. But anything we do can be used for good or bad. Yes? So as humans, it's our responsibility to put control on the bad and do better with the good. That's our job. That's our policy. That's what we elect people for. And that's what, as physicists, we have to tell them who we elect. This is a good thing and this is a bad thing. It's your job to put rules that will control the bad and allow the good to flourish. That's our job too. So we have to educate people to do that in the future. As we develop more, we do not know what dark energy and dark matter is. But probably it's most of the universe. So when we discover what dark energy and dark matter is, it will have bad consequences too, just like nuclear energy has bad consequences. But we can use nuclear energy and stop global warming. Global warming will stop if we use nuclear energy. But nobody wants to use nuclear energy because everybody's scared. And that's not a good thing, that's a bad policy. We should use nuclear energy because there will be no global warming. But we don't want to do that too because Indonesia exports a lot of oil, right? We don't want to do that too. So we have to be careful as policymakers. So we have to balance the good and the bad. It's our job to educate the people to balance the good and the bad. Okay. So yes, everything has a bad thing. For example, when humans learned how to make metal, when they decided 10,000, oh well, not 10,000, when 2,500 BC, when they decided how to make copper, they could use knives, they could make knives out of copper, or they could make a sword out of copper. So they do both, yes? So human progress has, with technology, anytime you develop science and technology, is always a good and a bad. As a society, it's a responsibility to control the bad and do the good. So we have to make the rules. There is no such thing like everything is good. Nothing is good. And nothing is completely bad until we figure out how to use it. Does that answer your question? Okay.
We have still 5 minutes more, so any other question? No question? Okay, okay, please.
Great talk, so informative. So my question is, the question from Professor Tasri. Where about this budgeting, right? Yeah, budgeting.
Budgeting. Okay.
To support, which be supported, and then I don't know whether it's decided by the Senate in US, because here the budgeting is decided by the Senate, and then, for example, me, I'm working on black holes. It's always difficult for me to find the topics that I can get in because it is not covered. For example, like normally like 7 topics, black holes not in it. So I never been supported by any projects, by any funding, by my government. Despite I can safely say I'm quite productive. So in US, how does this work actually?
Very good question. So in the US, also, there's no guarantee. Okay, just to tell you. First, to answer the first part of your question, how does the budget get decided? So usually in the US, the president makes a proposal, okay, of the budget. And then the Congress, which is the Senate and the House of Representatives in the US, makes the budget, okay? But the US proposes, and for example, in this year's budget, President Trump has proposed a big cut for all the science, okay? But I'm very confident that the Congress will reverse this, okay? So this happens a lot in the United States, okay? So once the budget is decided, then it goes to the funding agencies like the National Science Foundation, which then decide on the priorities, based on the priorities. Now, as usual, we are all humans, which means that the funding really, at some level, there's a lot of politics that intervenes in the funding. We are humans, so we have to understand this. So. But there are priorities decided, and if you have a big impact, sooner or later you will get funded. And I mean sooner or later, not always. Okay? Not always. Okay, not always. In the U.S., if you write 10 proposals, you can get funded for 1. Okay, so the funding rate is very hard, 10%. It's not easy. But if you don't have funding, you will not have a job. Okay, in the U.S., so it's a very competitive research environment. Okay. But there's a recognition that if you're productive and if you're writing papers with a lot of citations, you will get funded. Okay. Unlike many other places where politics is very more important, which means name recognition is more important than your productivity. In the US, in human relations, politics is always important, but merit counts for a lot. And you will get funded if you are productive. Does that answer your question? But it's not easy. It's not by any means. Yeah.
Okay, thank you very much, Professor Umar. Please give applause to Professor Umar.